In Oklahoma, a deadly disaster on a major freeway.
Driving along at 70 miles an hour and the whole world opened up.
In the UK, the Royal Air Force races to save a town.
They were huge concrete slabs smashed apart by the water. The dam could have broken at any time.
Near New Orleans, a devastating explosion rocks a community.
The silos were in flames, and there were helicopters lifting men off the burning silos.
And in Australia, tragedy strikes on a runaway train.
I kind of remembered a bang. Next thing I came to lying on the window on the other side of the train.
With big builds, even the smallest mistake can be a huge disaster. From miscalculations to misunderstandings, some with deadly consequences. These catastrophes are every engineer's worst nightmare. Engineers constantly strive to build bigger, bolder, and crucially safer structures. But sometimes catastrophe strikes when and where you least expect it. Like this deadly disaster in Oklahoma on one of the state's busiest crossings.
It just collapsed right in front of me and people were driving off into the river.
A catastrophe that took down a vital bridge.
We had no idea how many people we had in the water, how many vehicles. Nobody knew. It was quite a shock.
And a devastating tragedy that took everyone by surprise.
Nothing's indestructible. Everything has got its limits. We can break anything.
The Arkansas River is Oklahoma's largest waterway, and for small towns along its banks like Weber's Falls, it's all about enjoying the great outdoors. Norman Barton Jr. is a lifelong resident.
I grew up on this river, fishing, hunting all around it all my life. My dad used to tell stories about changing my diaper in the boat. This is home to me.
The Arkansas River is fantastic for more than just recreation and fishing. Every year, around 12 million tons of cargo are transported up and down the stretch of water.
We're in farm country. We're in coal country, steel country, all that, and it all travels up and down this river. And it's amazing if you sit out here and watch these barges. It's commerce at its finest.
And it's not just the waterway carrying cargo. Crossing the river is the I-40, a vital road link around 3 kilometers south of Weber's Falls.
The I-40 is the third longest interstate in America's highway network. It runs more than 4,000 kilometers, almost coast to coast, from California all the way to North Carolina.
The bridge was built in 1967 to keep traffic moving above and below. 4 lanes for vehicles and a nearly 100-meter wide shipping channel with the bridge towering over 18 meters above to allow larger vessels underneath. Former Fire Chief Jack Shackelford remembers it well.
Actually, I was growing up down here when they built the highway and the bridge. They had to raise the bridges for the tugboats and the barges, and they rerouted the highways. Interstate 40, it was one of the major interstates through Oklahoma at the time when they first built it.
The more than 600-meter-long bridge sits on 12 reinforced concrete piers. No easy task, as Professor of Engineering Steve Tipton knows well.
They actually run those piers all the way down to bedrock. And they'll set a cage of reinforcement bar, dump a lot of the concrete in there, get these piers set in there. They, you know, when you look at them after they're up, you feel like, wow, that's indestructible.
Early morning, May the 26th, 2002, Memorial Day weekend. Norman Barton Jr. was competing in a fishing tournament south of the I-40 bridge. As Norman passed a buoy, he just happened to look up.
The bridge just actually collapsed right in front of me. Wow.
2 barges weighing more than 1,000 tons being pushed by a tug the Robert Y. Love had rammed into one of the piers 60 meters outside the main channel. The force of the impact caused a 150-meter section of the bridge to drop onto the barges and river below.
The next thing I know was cars driving off of it. They're driving along at 70 miles an hour and the whole world opened up. The bridge was gone and people were driving off into the river.
With cars and trucks in freefall, another fisherman grabbed his flare gun.
It just shot an orange stream up over the bridge and actually hit a truck right on the windshield. Just boom, and went up in the air. Well, that trucker jackknifed his truck on the highway, and that stopped traffic.
Quick thinking combined with a 1 in a million shot ground traffic to a halt. Former captain of Muskogee Fire Department, Jack Shackelford, was just coming off the night shift when he overheard a 911 call.
I heard the dispatch inside the station that there'd been a collapse at the Interstate 40 bridge in Weber's Falls, and I couldn't believe my ears, and they were calling for all help. So I asked the assistant chief on duty if it was all right if we took the rescue squad and came down here, and he said by all means.
But as they arrived on scene, the sheer horror of what they were facing was daunting.
It was quite a shock. The ramp going up to the bridge was still intact, but when we got to the top of it, the bridge was just gone. Where the barge had actually hit it, the bridge actually fell down on it and was sitting and was resting on the barge. And we had no idea how many people we had in the water, how many vehicles we had in the water. Nobody knew. You don't know where to start.
11 vehicles had either gone down with the bridge or driven off the freeway into the river. Norman found a truck driver trapped in his cab and about to go under.
He was just sliding, just trying to get a hold of anything before he went under that 400-foot boat.
Norman knew he had to act fast.
Tried to get a hold of his belt, but the current was so bad and he was just hanging on. But I finally got in the water, got a hold of him, and told my partner to get us out of here, get us out from under this thing.
But not everyone was so lucky. Rescue divers and anglers searched desperately to pull out anyone they could find.
Friends of mine that were pulling a guy into their boat. I mean, we looked, there was nobody else that could be saved. Nobody ever came up. There was only 3 people that you could actually saved, and we got them.
For Jack and the other teams, it was clear no one else was coming out.
We had to shift from being a rescue to total victim recovery. But it took all 4 days to get all the vehicles, to get them located, get them pulled out of the water, and to get the victims extricated from them.
Of the 19 people who went off the bridge, 5 survived, but tragically 14 died.
It's been a long time since I came by here with all these thoughts in my mind. I wasn't expecting to get emotional again like this. It's kind of bringing back some not so pleasant memories, I guess.
In the aftermath of the disaster, the first question was how had the Robert Y. Love missed the 100-meter wide navigation channel by so much?
Although huge, the barges were still only about 1/3 of the width of the shipping channel. The captain himself said it was easy to navigate and he'd safely done it hundreds of times. So the question was, what happened this time?
It turned out that while maneuvering the tug and barges to pass under the bridge, the captain of the Robert Y. Love suddenly lost consciousness.
Effectively, no one was steering, and the boat kept pushing the barges west out of the main channel, straight towards one of the bridge piers.
The barge left the river channel and actually hit this pier right here, knocked it completely down.
I don't know if he blacked out or passed out or what, but when he struck it, it just collapsed like a domino effect.
But how could one tugboat with 2 barges, traveling at around 10 kilometers an hour, take down more than 150 meters of concrete and steel? Professor of Mechanical Engineering Steve Tipton explains.
Nothing's indestructible. Everything has got its limits. You know, that material is just a bunch of atoms holding hands. If you push them hard enough to break their grip, they're going to come apart. That's kind of the way it works.
The culprit was the very material that gave the bridge its strength: concrete.
Concrete's brittle. That's a problem with it. But brittle material has a benefit that it can take compressive loading really well. The road's heavy and it's carrying that weight, and then vehicles go over it a lot and it's carrying that weight, but that's not a problem for those big columns. But if you give it just even a very light impact load, you can't handle it. That's just not what concrete's for.
These piers can easily carry the weight of nearly 20,000 vehicles rolling over them every day, but they're not designed to take sideswipes from massive barges.
These are just blocks made out of concrete. I can put it like this, and I can stand on this guy, and you know, it's plenty strong enough to take that load, right? But even with just a little bit of an impact load, there's just not much. Just tap it, you practically tap it, and it goes. That's a pretty good example of how intolerant concrete is to impact loading.
While the main piers beside the shipping channel were protected by steel and concrete islands on the upstream side, all the other concrete piers had been vulnerable to impact for decades.
Concrete's got a lot of pores in it. Pores aren't a big deal in compression. The problem with them is that if you simultaneously give them a side load, any kind of a crack or a pore or a flaw will just take off. And now it's got this huge weight on top of it too, and you're done.
With a vital road link gone, the bridge needed to be rebuilt, and fast.
It was absolutely amazing how quick they rebuilt this bridge. They ran crews 24 hours a day up here and rebuilt this bridge. I mean, literally pulled it out of the river.
Just 65 days after the tragedy, on July the 29th, 2002, the bridge was reopened, but this time with protection cells in front of all 12 piers, so that any wayward vessels would hit a cell and be stopped before it could damage the bridge.
When you've got a hazard, you have a responsibility to do something about it. So the number one thing you do about it is you try to prevent it. So that's what the barriers are for. They're sort of number one line of defense.
With the bridge piers now protected from all angles, the hope is that no barge or ship can ever threaten the bridge again.
A year after the disaster, a memorial was erected dedicated to the memory of the 14 people who sadly lost their lives.
This one was tough. It was really tough. It affects you. I mean, there's no other way to put it. It affected everybody.
You know, it turned into a terrible tragedy in a split second. But I was glad to be where I was at the time. I didn't want to be, but I was. Just the right thing to do.
When it comes to big construction, engineers are constantly striving to overcome the overwhelming forces of Mother Nature. Get it wrong and the results can be catastrophic. Like this disaster in the UK, a dam on the brink of total collapse.
You've got 1.3 billion litres of water spilling through the entire town.
Mass evacuation as an ancient town's future hangs in the balance.
Time was running out, the village would become the biggest disaster since wartime history.
And the Royal Air Force rides to the rescue.
Clearly, the dam could have broken at any time. It was unfathomable the amount of destruction that it potentially caused.
The Peak District in England is one of the country's most beautiful hotspots.
The Peak District is the UK's oldest national park. Thanks to the stunning countryside, it's also one of the most popular, attracting more than 13 million visitors a year.
This rugged hill landscape gets high rainfall, and dams are a regular feature. Some are used for power, others for flood control. But Toddbrook Dam above the town of Whaley Bridge was originally built to feed a canal. Les Eckersley is a local resident and amateur photographer.
The Toddbrook Dam was built to supply water to the canal system that was used to transport coal and stone from the local quarries, so it's part of the UK's history.
During the Industrial Revolution, canals were vital for moving goods all over the UK. These man-made rivers had to be regularly topped up, so reservoirs like Toddbrook sprung up all over Britain.
Originally built in 1840, Toddbrook was made up of a solid core of watertight puddle clay, surrounded on either side by a much larger embankment of compacted earth. Dr. Andy Nichols is a water engineering expert.
That compacted earth provides mass and it provides strength to hold back the weight of the water that's behind it, while the puddle clay core is the waterproof part that prevents the seepage of water through the dam and onto the other side.
In the 1960s, a new spillway was built to carefully control the release of water in the event of flooding.
The reservoir can hold more than 1 billion liters of water, the equivalent of around 450 Olympic swimming pools. So like any dam, its spillway is crucial.
Made of large concrete panels 15 centimeters thick, the roughly 75-meter-long spillway was constructed over the central part of the dam by adding concrete capping to the earth embankment.
The spillway is designed to let large volumes of water escape from the reservoir in a safe way. In designing the spillway, we need to consider what's called the maximum probable flood, and we need to make sure that we design the spillway with the capacity to be able to discharge that amount of fluid without anything going wrong.
Late July 2019, heavy storms began raining down on Whaley Bridge and the Toddbrook Reservoir. Even for locals used to the British weather like Les, this was unprecedented.
This path we're on now is actually running at the side of the River Goyt. Would be underwater now. That's how high the water was. Typically, we do get a lot of rainfall, but that was pretty extreme.
While bad weather was forecast, this was relentless, with 2 separate storms dropping more rain than this area had seen in decades.
We saw a 1 in 43-year storm, closely followed a couple of days later by a 1 in 92-year storm. And that resulted in a lot of water flowing into Toddbrook Reservoir.
The reservoir was at capacity and the spillway was hard at work.
In all the time I've lived in Whaley Bridge, I've never seen the actual spillway in action. It's a spectacular sight. I had to photograph and video it.
But while it might have looked spectacular, the spillway was struggling to cope. As engineers began pumping water out to reduce the reservoir's dangerously high level, it dramatically revealed the full extent of the damage to the spillway.
I could see that quite a few panels had collapsed and there was like muddy liquid running out of the dam.
As the hole got bigger, the structural integrity of the dam was under threat. A full-scale emergency was declared and 1,500 people immediately evacuated.
I thought it was just going to get worse and worse and just basically wash away and the village would be gone. The village would have been flushed away.
If the dam failed, more than 1 billion litres of water could engulf the already flooded town. Their only chance was an emergency plug in the spillway to hold the embankment in place. It was time for drastic action. It was time for the Royal Air Force. Flight Lieutenant Matthew Smith and his helicopter crew swung into action.
We've been briefed that the Toddbrook Reservoir had been damaged. We knew we had something to move. The success of the mission would be quite critical to how quickly we get up there and provide the services. Our minds really, it was just trying to get underway so we could offer our support as quickly as possible.
As they reached the dam, there was no time to lose. The side of the spillway was now completely undermined.
They were huge concrete slabs smashed apart by the water. And clearly, the dam could have broken at any time.
With a last-ditch plan to add structural integrity to the dam, Matthew and the crew would have to drop hundreds of one-ton bags of rubble, 6 at a time, directly into the hole. A risky and uncharted operation.
The pilot had to hover this mammoth helicopter and its load directly over the damaged section of the dam.
If they missed the hole, they might smash more slabs, risking the integrity of the entire spillway.
The feeling of dropping 6 tons from an aircraft when you've never done it before, it's really quite unique. As soon as you press that button and release, you've got about 30% worth of power back from the engines, and that's an immense amount of power from the engines that this aircraft has.
These twin-rotor helicopters can carry more than 50 troops or 10 tons of cargo, no problem. But crucially, they normally have somewhere to land. Here, hovering so low, if something went wrong, there was nowhere to go.
In total, Matthew and the team dropped 600 tons of rubble and around 1,000 sandbags, successfully plugging the hole, saving not only the 188-year-old dam, but the town of Whaley Bridge.
The amount of destruction that this dam would actually cause if it did break, with 1,500 people living below the reservoir. For the mission we were trying to achieve, it couldn't have been any better.
The precision of the flying, there isn't many people in the world that can fly helicopters like that. We had a very lucky escape that day. Very lucky escape.
As the rains died down and people returned to their homes, everyone wanted to know how this disaster could have happened.
The concrete spillway was subjected to a torrent of fast-flowing water. But that's what it's designed for. So the big question was, why had it failed so catastrophically?
The UK government ordered an immediate investigation. They discovered a crucial part of the spillway's defence was missing, known as the cut-off wall or beam.
So we have the crest slab that sits on top of the dam, and then typically there would be a cut-off beam that penetrates from that crest slab and joins it onto the puddle clay core of the dam, meaning that there's a solid barrier that prevents any seepage of water through. But in this case, the original design didn't have one of those.
The cut-off beam acts as a barrier, connecting the crest slab with the waterproof clay core. Without it, water can penetrate under the spillway, washing away the earth, holding the concrete slabs in place.
A cut-off beam is like the sealant, plugging the gap between your bath and the wall. It's a similar thing here, only this time there's a lot more water with a lot more force that can do a lot more damage.
It was actually one of the lower slabs that moved first, probably because of the water causing sufficient pressure to lift that slab. And that was really the point of no return. At that point, that's where we had substantial flow of water through that then caused the concrete slabs above to collapse in.
With this ancient design flaw, the extreme weather created the perfect storm and the dam failed.
It's estimated that the water eroded around 800 tons of embankment until there was virtually nothing left to hold the slabs in place. Thankfully, a Herculean effort saved the dam and the day.
If those efforts hadn't happened to reduce the water level and to shore up the dam, then it's quite possible the earth embankment itself could have been eroded away. And in that case, you've got 1.3 billion litres of water that are rapidly, in a case of a few seconds or minutes, spilling through the entire town of Whaley Bridge.
With the disaster averted and the water levels reduced, a new spillway will be constructed at an estimated cost of around £14 million. In addition, new proposals were put forward for the maintenance of the UK's entire ageing dam network.
Like Toddbrook, many of these dams were constructed more than a century ago. It's now recommended that engineers inspect them at least once a year.
And while the Royal Air Force frequently flies to the rescue, hopefully they'll never have to do it again, quite like this.
We train day in, day out, and 9 times out of 10 it is troops and operations, and I've flown all around the world. This is the first time I've ever done it in the UK, and seeing a difference and knowing that you're stopping that dam collapsing, potentially destroying people's homes, livelihoods, I don't think there's any other feeling like it.
With any structure, engineers walk a tightrope between function and safety, but sometimes getting the balance right proves impossible. Like this tragedy in Louisiana that ripped through the heart of a community.
The silos were in flames, and there were helicopters lifting men off the burning silos.
A massive catastrophe triggered by something seemingly harmless.
You don't ordinarily think of a loaf of bread as a bomb.
A disaster that helped force a change in the rules.
The destructive forces at work here are truly unbelievable.
New Orleans, founded by the French in 1718, owes everything to the mighty Mississippi. Journalist John Pope is a lifelong resident.
The Mississippi River is the most famous river in the United States. You've got songs written about it, you've got books written about it. Showboat, Tom Sawyer, Huck Finn, Life on the Mississippi, and that's just for starters.
But there's a lot more to the Mississippi than its cultural legacy.
The river is continually busy with maritime traffic. Everything comes down the river to New Orleans and then out to the Gulf of Mexico and the rest of the world.
One of the most valuable goods is grain.
Every week, almost 1 million tons of grain, like wheat and corn, is barged down the Mississippi. That's 60% of the nation's grain exports.
And key to moving it all are massive structures called grain elevators. This giant facility at West Wego, just upstream from downtown New Orleans, was first built in 1960, and today stores over 4 million bushels of grain. Although vast in scale, the process is simple.
Essentially, a grain elevator scoops grain from the bottom of the barge up into massive storage silos. At its heart is a constantly operating system of conveyor belts and bucket lifts.
Engineer Tim Duncan is an expert in the design and management of marine terminals.
Transport the grain to what we call a bulk scale. Bulk scale weighs the grain and deposits it onto another belt conveyor that then transports it across the levee to this head house, ultimately to belt conveyors that deposits grain into individual silos. In essence, it's barge to silo, silo to ship. There's only a little bit of process. The grain that is shipped out of these facilities essentially feeds the world.
West Wego has been home to grain elevators since the late 1800s, playing an integral part in global grain supply. But it's also the site of an event that forced this massive industry to change forever. December 22nd, 1977, West Wego grain facility operations were underway, and employees were looking forward to the holidays.
Continental Grain had a custom of giving turkeys to its employees. So a lot of people had come to the grain elevator and pick up their turkeys.
But around 9:05 a.m., the festivities were suddenly cut short as a massive blast shook the city. Journalist Bruce Nolan was at home at the time.
I heard the deep, deep concussive whomp, completely irregular, clearly something badly wrong.
The giant grain elevator at West Wego had exploded. Journalist John Pope rushed to the scene.
When we arrived, the silos were in flames, and there were helicopters lifting men off the burning silos.
First of all, I see enormous plumes of smoke. I can see the tops of the silos. They're topped with wreckage. Black smoke is pouring out the top of the elevator.
A powerful blast had completely destroyed the 25-story grain elevator.
It's a mess. It's completely wrecked. It's so badly mangled that it doesn't even compute. I've never seen a concrete structure this massive broken like a child's toy.
The tops had been blown off 48 of the giant silos.
People who witnessed a blast across the river, they watched debris from the blast arcing into the sky and dropping all up and down this stretch of river.
Rescue crews worked tirelessly day and night, but tragically 36 people lost their lives. Only 11 survived. This was one of the deadliest industrial disasters in American history. Yet the machinery had simply been moving and storing grain.
Many times people don't think that a grain elevator, which handles corn and wheat, can be explosively dangerous. But they can be. They are very dangerous.
Operators have long known of its highly volatile qualities, and it all comes down to tiny particles of grain dust.
Any transfer from conveyor to conveyor accomplishes a couple of things. It not only damages the grain is relatively fragile, it also produces dust.
Grain elevators are scooping and pushing and shoveling and disturbing and agitating thousands of tons of wheat, corn. The dust is billowing into the air from the operation.
More explosive than gunpowder, confining enough grain dust within one place can be deadly.
If you take a loaf of bread, you divide it into tiny motes of dust. Each one of those tiny motes can burn if subjected to ignition. When a billion motes of dust all ignite at the same instant, that's the definition of an explosion.
An explosion like this needs 4 key ingredients. Fuel, that's the grain dust, oxygen, which is all around it, a confined space like a bomb casing, here that's the concrete structure, and then all you need is a spark.
Pinpointing the exact source of the spark among the devastation was impossible. But one obvious suspect was the elevator system itself.
My understanding of the explosion in West Wego is that there was a problem with the bucket elevators. And a bucket elevator is a series of buckets that are bolted to a conveyor belt with pulleys at the top and at the bottom. Perhaps there was a belt misalignment, a pulley, which caused either a spark or a hot bearing or a fire that ultimately lit the chamber and caused the explosion.
Some also questioned whether a recent change in regulations may have been a factor.
Grain dust in the atmosphere is a known health hazard. It causes multiple respiratory problems. In the 1970s, the Clean Air Act came into force, and buildings had to be made more airtight to better contain grain dust.
Vacuum systems had been installed to recycle the dust, and ventilation in the elevator and silos where dust could previously escape was closed up.
At the time, some questioned whether the new regulations had made things worse. First, there was more dust, or fuel, inside the structure than before. Secondly, and more crucially, it was more confined. When it went, it was truly like a giant bomb going off.
Following the disaster, new industry guidelines and national regulations were introduced for the containment and controlling of grain dust at elevators.
All the motors are in the right atmosphere, are explosion-proof motors. There's even lightning protection. Even your phone isn't allowed unless it's wrapped in an explosion-proof case.
More than 4 decades later, the elevator at West Wego continues to process grain, standing as a memorial to the people who lost their lives on that terrible day.
I spent a career as a newspaper reporter, and you see a lot of bad stuff. But if I think back about all of the really shocking, spectacular stuff, this Continental Grain Elevator explosion still belongs somewhere on page 1.
In big engineering, planning for every eventuality is a key consideration. But sometimes even the best laid plans can go disastrously wrong. Like this catastrophe in Australia on an out-of-control commuter train.
I kind of remembered a bang. Next thing I came to lying on the window on the other side of the train.
This tragedy revealed a flaw in a vital security system.
90 seconds after departure, it was an unguided missile. It looks as though the train ran away.
And forced a change in the safety regulations. The Royal National Park, just south of Sydney in New South Wales, is the 3rd oldest national park in the world. In the 19th century, the small town of Waterfall sprung up on the outskirts as a camp for workers building the Illawarra rail line.
The Illawarra line was built in the mid-1800s to connect mining and farming businesses with Sydney.
Laying a rail track through the rugged landscape was a major engineering challenge. Railway operations analyst Alex Wardrop explains.
The great difficulty is that you have to cross the Illawarra Escarpment, which is very steep. And so the railway was built on severe grades with lots of tunnels.
Building a track through the carved-up terrain wasn't easy. Cuttings, tunnels, gradients, and curves pushed rail engineers to the limits.
The terrain wasn't just a headache for engineers. It's a challenge for both the train and driver.
Trains work best on straight and level tracks where they can run smoothly and the driver can see what's coming ahead. As soon as any curves and slopes are involved, things get more complicated.
The issue about driving trains is that you have to be aware of your gradients and speed limits. Trains don't have very good braking compared to road vehicles.
Despite the slopes and curves, trains safely navigated the tricky route for more than a century. January 31st, 2003, an early morning Tangara-class passenger train was heading south from Sydney to Port Kembla. Shortly after 7 in the morning, the train passed through Waterfall. Journalist Noni Walsh was heading home.
I suddenly noticed that the train was going a little bit fast, and you could see people going, that's a bit odd. And I kind of remembered 2 corners and maybe a bang, but that was the last thing I remembered.
At 7:14 a.m., about 1.5 kilometres from the station, the 4-car train with 47 passengers on board derailed. South Sydney Fire Rescue Chief Superintendent Paul Bailey was on his way to the station house.
I was driving to work and over the radio heard the call about the incident at Waterfall. I was 10 minutes away, so I responded to the incident.
As Paul arrived on the scene, it was clear that a major disaster was unfolding.
We saw the back half of the train still intact and still on the rails, but as we walked closer we saw the first couple of carriages had actually derailed and toppled over onto their side. We weren't sure at that time how many people were trapped or indeed what the situation was.
Among more than 150 tons of mangled metal, Noni was a trapped passenger and injured.
It was pretty eerie and quiet when we came to. I blacked out, and apparently that's a good thing because my friend told me later he was actually on his knees on the window watching the rails go past, terrified. And I'm so glad I didn't see that.
Paul and the other rescue crews swung into action,
It was quite traumatic for those people because not being able to get out of the train, they don't know if it's going to catch fire, they don't know what's going on. So our major concern was to ensure that those people were removed and get them away from the scene as quick as we could.
As Noni was pulled from the train, she realised the full extent of the devastation.
And it was really only then that we saw we were in something much bigger than we really knew about. It was, yeah.
Of the 47 passengers on board, 41 were injured in the wreckage. But tragically, the driver and 6 passengers died. This was a regular route with more than 50 passenger trains a day. An investigation was launched to find out what went wrong. Rail operations analyst Alex Wardrop was an expert witness.
The accident was unusual in that there was no collision or anything, and yet 90 seconds after departure from Waterfall, the train was a crumpled mess.
With no obvious track damage, investigators turned to one of Australia's leading engineering software companies. Technical director Dr. Jindong Yang and his team created an accurate simulation of the event.
We were tasked to simulate a number of scenarios to determine the most likely cause of the accident.
Running the simulation at different speeds revealed a key piece of information. Instead of slowing down, as the train approached the curve, it was gaining speed at an alarming rate.
The speed limit around this cutting was 60 kilometres an hour, but when the train took the curve, it was travelling nearly 120.
That made the train turn over and derail. The wreckage, the simulation showed very similar amount of damage on the carriages to what really occurred.
After it started to accelerate, it just continued to accelerate, and gravity did the rest. So by the time the train reached the critical left-hand curve, its speed was such that it was an unguided missile. The train rolled somewhere between 117 and 118 kilometres an hour.
But one big question remained: why was the train going so fast in the first place? It turned out that before the crash, there had already been a tragedy on board. The driver had suffered a heart attack.
Before the accident, the driver, unfortunately, had died.
But trains like this have safety systems in place to trigger an emergency stop, the so-called dead man's brake floor pedal.
The dead man's brake is a safety switch that stops the train if the driver becomes incapacitated.
If he let go, the brakes would be immediately applied, and that didn't happen.
The investigation discovered that there was a flaw in the fail-safe system. As the driver slumped forward, instead of releasing the dead man's pedal, his weight was still pushing down on it.
So it didn't matter if he'd slumped off, the driver safety device didn't cut in. And so it was clear then that the cause of the accident was the driver safety device did not detect that the driver was incapacitated.
And this wasn't a one-off failure. Further analysis revealed that all Tangara-class trains suffered from the same problem. After the disaster, new fail-safe switches were designed which would automatically hit the brakes if there was no response from the driver, safeguarding against any repeat of the tragedy.
That was inevitably the root cause of it. The dead man's handle didn't recognise that the driver had had a heart attack, and it allowed that train to continue to accelerate. They changed significantly the way that their dead man handle worked on the train, so I think that was a good thing.